Good morning. We're letting you know that the broadcast is starting. We're waiting until the top of the hour for full things, but if you want to make sure that your system's actually working, I figure I should say something so that you know that that part of it's working. Hopefully you should be able to see a title slide. This is Todd Hallahan from Oklahoma State University in Aestus, and we should have a title slide and you should be hearing something right now. So if those things are happening, all is good, and we'll start in about a minute here.
And here we go, it's top of the hour. Thanks, Todd. Well, welcome everyone to the 30-minute case study webinar series. This is John Sankey. I'm an engineer for TrueBlue Technologies, and TrueBlue is a sales engineering firm that represents 4 companies: Aestus, Tersus Environmental, TRS Group, and West Bay Instruments. Over the next 2 months, we have a series of 4 different speakers, one from each of my principals, discussing case studies that focus on the topic of managing complex sites with high resolution, site characterization, and focused remediation. Today, we're very pleased to have Todd Hallahan discuss the first case study about a successful LNAPL remediation in less years in Karst via the scan-first approach. And Todd will explain how this scan method works. Todd is a professor and the Sun Chair of Hydrogeology at Oklahoma State University and serves as the Chief Technical Officer for Aestus. As the NGWA, or National Groundwater Association, McElhaney Lecturer, Todd gave talks all over the world in 2018. So thank you, Todd, for presenting this case study. You are now the lead.
Thanks, John. And so I don't have to walk and chew gum at the same time. I've got somebody else running slides for me, so I'm going to just tell them to advance the slide in case you're wondering why I'm doing that. Makes it a little easier versus trying to do both at the same time. So I lead a life with a managed conflict of interest. So as a professor, I'm working with grad students to learn how to do new things, and then as a chief technical officer, managing the technology as it goes out to market. And so I sit on the line between that. So if you got questions on how that works, just let me know, and I can tell you those sorts of things. So next slide. So we're trying to be respectful of your time, so we're trying to do this in 30 minutes. If that's the key reason you joined us because, hey, it was under 30 minutes and that's what I wanted, give us that feedback so we have an understanding of whether you would like an hour webinar or whether the 30 minutes was the key part of it that you really liked. We're going to address the questions at the end of the slides, and then there's a chat function to submit your questions /chat function to submit your questions. And at 30 minutes, you're welcome to duck out. We will be done with the basics, but we'll be sticking around for additional questions at the end. So we're not going to cut you off at that point. Feel free to ask many questions as you like. This is being recorded for you. So if you need a copy of it or something, that'll be available. And then we're giving away a Starbucks gift card as part of this. So that drawing will be held later today as we figure out who all attended and things. You can increase your chances by submitting questions, and by the end of the week, you get a notification of who was the Magic Gift Card giveaway person. A lot of times we do webinars and things, we buy pizzas for people and stuff if we do those things. So this is the rough equivalent that we can do in COVID time. Next slide. So if you're doing site characterization, when you walk into a site, and this is, walking into a bedroom and seeing an issue, when you go characterize a site, you got to decide whether it's a problem or not. Some people don't have a problem with the dog being on the bed, some people do. And so you got to decide if there's a problem that needs to be fixed. And so is there a receptor? What kind of problem we're dealing with? And so there's a first level question of, hey, do you really need to do something? Are you guys going to be remediating things, or we just need to do a basic check? And so that's the first question. And it's not, hey, how do we remediate this? It's, do we need to do anything? And that's the first level check. Next slide. Once you've decided you've got a problem, then you start thinking about characterizing a site. So you might have a porous media problem, you might have fractured media, you might even be in karst. And so you've decided, yep, I've got a problem, and I think about this with medical analogies. Okay, we need to go do surgery, right? So you might have gone to the doctor and they said, nope, here's a pill, go away, you don't have to worry about it, this is cheap. Or they go, we're going to send you into surgery. And once you decide that, it changes what the problem is. And so if you decide you need to remediate, that tells you that you're going to be spending real money in terms of trying to fix up the subsurface in 3D. And that puts you into a different category than just, let's just see what's happening. Next slide. So if we think about that relative to a vet doing that, if you go into the vet, takes a little blood sample, checks out the dog, $100 bill to figure that out, and they go, yeah, you can go on home. Or they say, okay, the dog's going to need surgery. They might say, hey, we want to do a scan, check an MRI, look at it first before we go in for the surgery. And the cost of that's a lot more than the original characterization. But you go, well, but it's a lot cheaper than doing surgery, and I don't want to screw up the surgery. So the cost of a scan in the middle of there makes a lot of sense. On the environmental side, it's basically the same sort of math is, hey, we did a quick check, but now we're going to need to do surgery. Should we do a scan first and look around before we go in for surgery to make sure the surgery is successful? And people, when they look at different technologies, when you get into high resolution site characterization or ultra high resolution site characterization, it's an added cost for characterization that people normally don't spend. But the backside of that is, well, you could do remediation for much more money, go through the surgery and have it fail, and then go try something else. Or maybe have it work, but maybe it takes 20 to 100 years, in which case you're spending so much money on the backside that spending additional money on characterization is well worth it. And I've seen some different estimates, something like $17 to 1. I've seen different combinations of how much it's worth it to invest in characterization per dollar versus the cost of remediation. So if your patient needs to have a surgery, going in and getting an MRI ahead of time is not a bad idea. Next slide. So when you're thinking about high resolution or ultra high resolution site characterization, you're thinking about, hey, I've got things in 3D in the subsurface. I need to go fix that, and you need to know where it's occurring at. So when I work on impacted sites, hey, do we have a second source? Do we have more than 2 sources? Do we have preferential pathways? When did the source actually go on the ground? Is it degrading? All these sorts of things. And you decided, hey, we're going to do surgery. We've got complexity. Let's get up to high density data and look around. When you do that, now you're going to have a lot more data to manage, and you're going to need to survey where you're at in space. The little map with there's the building and there's a tree behind it. We drilled a hole near there. Isn't going to cut it when you go up to these kinds of data sets. And so you need to manage the data sets, and then you also need to do 3D visualization to be able to look around with those data sets. You can't, no matter how good you are at 3D in your head, you can't pop 10,000 data points in your head and rotate them around and think about them. But computationally, you can do that in a computer quite well now. So you can either do a high resolution site characterization, which is sort of one-dimensional, and we can get lots of well points quickly with like a lab on a stick, or in this case, we're talking about ultra high resolution, where we're going to scan from the surface, look around down in the subsurface, and figure out what our targets are in our patient, the same way somebody would do with an MRI or an X-ray. Next slide. In terms of the protocols for that, it's the same as if you went in for any other medical procedure. So you're going to take the patient's history, you're going to do the scan, you're going to biopsy it and go, hey, what's next to the liver there? That thing looks funny. Once you've got the biopsy, you know what you're working with. You integrate all that data together to decide what to do with the patient. And now you're going to be making business and technical decisions that are quite effective because you got enough ability to look around. But you can't just take the picture and then go, hey, there is something funny next to the liver. What should we do now? Do you know if that's cancerous? No, we got to take a biopsy. The basic procedures, the scans will tell you a lot. It'll tell you where to look, but you still got to go in and demonstrate it is or isn't cancerous, and what are we going to do next? So that's part of the protocol. Same thing on the environmental site. We're going to take the images, look around, but you still need to biopsy and demonstrate what the chemistry or biological effects are at that location to be able to make effective decisions. Next slide. Now, in terms of this kind of work, I've been doing this for about 20 years. And so I started out as a physical hydrogeologist, used Darcy's Law. You learn that stuff in the classroom about how groundwater is going to flow, and you're going to figure it out doing well points and measuring chemistry and physics of what's happening in the groundwater system. This is same math. You're going to use Ohm's Law, and you're thinking about where things are more conductive and resistive and what that means about the structure of the subsurface and what's happening down there. So the benefit of physical is you get a direct sample. The benefit of electrical is you can get a lot more data and look around and be able to understand the subsurface that way. So the electrical tends to be referred to as a geophysical technique, but as far as doing electrical hydrogeology, you do geophysics with a sampler when you stick it in a water sample and get the EC of the fluid. That's a geophysical experiment too, but you don't care about how the EC probe works. What you want to know is, what's the property of the water that's going to tell me something about the subsurface? So as far as geophysics is concerned for scanning, what you want is that technique to be as boring as possible. You don't want interesting geophysics at all. You want an environmental sample, the same way as a benzene sample or an EC sample is as boring as possible relative to how you got it. You're more interested in what the numbers are telling you about the subsurface. Next slide. There's some lessons that come out. I got 5 lessons that I'm going to show you about doing electrical hydrogeology versus regular one. So this is the Cape Cod site up in Massachusetts, and the lesson here is, in a homogeneous isotropic setting, or as close as you can find to a boring sandbox, about 10,000 points are needed to figure out what the subsurface says. But on your average gas station, dry cleaner, or any other contaminated site, brownfield that you work with, it's going to be more complicated than this in the subsurface, and there's no way to do this. But in terms of the concept of data density, it tells us data density has to be about this magnitude. So electrically, you can walk into a site and collect between 10 and 100,000 data points pretty effectively. On a well basis, you're not going to be able to do that. You're going to be between 10 and 100 data points as an effective number versus the right scale for what you need to do on a technical basis. So you've got to marry these things together to get to the right data density. Next slide. In terms of scanning, it's not a magical thing. Sci-fi shows there's magical parts, but if we go into the medical industry or the oil industry, scanning has a context that you can look at how it works. The medical guys have a super easy case because all the bodies are roughly the same, and so they're scanning the same aquifer all the time. The oil guys have it a little bit trickier, except for they don't have to deal with anthropogenic things. Nobody buried anything in their site. So ours is a bit more complicated than both those, but if you look at scanning technologies, the guy on the left had a little problem with his vision was a little blurry, and he wasn't sure why. And he went to the dentist because his roof of his mouth was a little sore too. And the dentist immediately after taking an x-ray could tell him that I'm not the guy for you. And that kind of detection with scanning is what people think scanning is always going to be, that you need no technical capabilities whatsoever to determine that the guy has a nail in his head. Scanning tools do that, but they also can answer questions like, hey, does he have a bone cancer, or does he have a bad molar? And that takes more expertise in reading the data and figuring out what it means. And for most environmental sites, that's what it is requires some ability to read electrical data and marry that together with other data sets. Sometimes you find a nail in their head, but most times you're trying to figure out whether their molar is rotten. Next slide. In terms of being cheap, it's not cheap to scan people, whether you're doing an MRI or whether you're scanning environmental sites. So if you're going out and taking data on the subsurface, you can go out a drill crew and do a couple people and do that. This typically takes a crew of 3 to 4 people to go out. And that's if you don't have to do traffic control and go across streets and do all that kind of stuff. This is collecting data in real environmental sites. So you've got to think about how you do that. And you can't avoid those costs, but it's a lot cheaper if you only have to do one remedy and it's targeted versus, well, the first remediation didn't work. We're going to try something new now. And we still don't have enough data to see what's going on, but we're going to hope for the best. And we work on a lot of sites that people for 20 to 30 years have hoped for the best and failed. So looking around and getting the right data density is pretty useful. It's just not super cheap. Next slide. We did this work a long time ago with EPA looking around and found gasoline, in this case fuel, at a little gas station in a small town. It didn't sit like nice layers on the water table. It sits like blobs. And so gasoline is a resistive fluid, and about 1 to 10 parts per million, we start getting a detection on the subsurface electrically, and that's due to that resistive fluid blocking off pore throats and making things more resistive. But that's unweathered fuels. Go to the next slide. And I call this the cheese getting moldy or the bread getting moldy. You start having a bunch of microbes start chewing on it. You took this resistive blob of NAPL and you start having guys chew on it. They're conductive. And so in this case, we're looking at a really moldy site. The whole thing has gotten very conductive. And you're looking at the guys that like to work with oxygen and nitrogen versus the guys that like to work with sulfate or they do methanogenesis. So those zones start to show up and they get very conductive. And we still have targeting capabilities, but we're not sampling unweathered bed. Now we're sampling really moldy bed. And so when you're looking at sites that things like to chew on in the subsurface, it provides a conductive signal, and you got to think about what you're looking at for microbial structure as well as for contaminants, and you got to think about all those bits and pieces. Next slide. So protocols are developed to figure out how to look at all this stuff. And the protocols, all the steps are really important. And people like to take the scan and go, okay, we're done now. We've seen what's down there. Tell us everything. You still have to go through the biopsy, and you still have to understand the chemistry and the biology of the subsurface in order to make good remediation decisions. So you can't get out of the biopsy, and people want to do that. But the steps are all available in terms of thinking about how to go through sites, and it's a successful procedure to do that, but you got to do all the steps. Next slide. So we're going to walk through a case with these steps. So this was a municipal supply well where they had 20 foot of casing as the casing for a 1,200 foot deep well. They ended up having diesel go in the well. It was the diesel that ran the pump for the well. So they didn't think about any impacts, and they got impacted by the well system itself. So they had free product down at 100 foot on the water table. There was a perched water table about 30 feet, and they looked in their well. They said, wait a minute, we've got feet of product in here. We're going to have to do surgery. And so they decided to do a scan technique instead of starting to poke holes down 100 foot, which are not cheap wells. The last quote I heard this week was about 17 grand a hole if you're drilling down through hard rock down to that kind of depth. So taking images might be a cheaper way to go to look around. So next slide. So step one, you get the historical data, which at this point for this project was, there's a well that's full of diesel. There's a football field for scale. And so you're thinking about those diesel tanks in this municipal supply well, and then a pit that got dug out of the material that was immediately at the surface. So that's about all that happened before we scanned the site. Next slide. So the data comes in. Now we're looking around at a large scale. We're getting a lot of variability. And when you look at carbonates, there's not a nice layered carbonate that has nothing interesting going on. There's fractures, there's, in this case, contaminants. There's all sorts of stuff going on. And so being able to read these diagrams and figure out where to target, that takes some expertise. But carbonates are great for imaging through because they have lots of electrical structure, and it tells you a lot about how it's built hydrogeologically. If you're trying to use wells, you just have, well, okay, we still have more carbonate. In this case, you got carbonate to 3,000 feet, and we have cracks every once in a while. But in terms of how things are connected and how shapes are going in 3D, pretty difficult. But with the scans, you can target much better. Next slide. So you integrate data, you can slice and dice data, look at different horizons, think about what's happening, and then you can go in and work with those data sets. But the data sets are very similar to working with a benzene data set. It's built to be environmental data. It's not built to be interesting geophysics. It's built that I can take and put those in space. I can look at how lines are crossing. I can think about all the different parts of the data, and I've got to work with it in 3D. So you got to have the ability to do the visualization part so that you can work with the data sets. Because in this case, we're dealing with over 10,000 data points plus all the well data. Next slide. So when you look at that, then you've got a data set that you've got it integrated. Now you go in and do the biopsy. And so next slide. So we're going to look at this line right by the impacts, and we're going to look at it in a couple different ways, but think about how to work with the data set. So you've got this impacted municipal supply well. We've got an image over the top of it. So next slide. And we get a data set that looks something like this. And so electrically, this site has a pretty wide range of conductance from below 25 ohm meters, which would be something pretty conductive, through over 2,000, which would be something pretty resistive geologically. And there's a couple giraffes for scale to get a sense of it, because they're always trapezoids. No matter how deep we're looking, we're working with trapezoids of data. And so when we look at that, you go, well, you told me that it could be conductive if microbes are chewing on it. And you've got this conductive purple thing in the middle. And you told me if it's unweathered, it could be resistive. And you've got that resistive burgundy thing sitting there. So which one is it? Which one do I target? And you go, well, it's downhill into the purple thing, so having stuff run down there is hydrologically makes sense. And let's think about where the tank is at relative to these features. So next slide. We integrate the data and we start thinking about it, and the excavation pit's sitting there, the pump is sitting there, and then the well's sitting there, and we start thinking about it, go, okay, I'm suspicious of the burgundy thing, but I'm still suspicious of the purple thing because it's downhill. Do we have a bunch of microbes chewing on something down there? So next slide. So we go into the purple thing and we find that the limestone's a bit, or it's a dolomite there, it's a bit weathered, but otherwise it's non-detect, so that's not a problem. And it's funny when you sample something off of somebody's liver and you come back and you go, it's not cancerous, people are usually excited. With this technology, you go, I didn't find anything. They go, well, I don't think this worked. You go, well, we did the biopsy and this one wasn't bad. Let's go biopsy the bad guy or the resistant guy. Next slide. So take those and we find that the high resistance and the middle one are both impacted at different levels. So next slide. And we also can look at the geology. So you've got a little soil zone and then an epikarst zone, and you can see that relative to the other data. If you did it with well data, you get lines. If you look at the electrical data, you see structure to it. So if you need to know the structure, you've got a lot more data to work with, but you're putting together the same hydrogeologic story, you're just doing it electrically. So next slide. So we can go in and put in the free product wells, do recoveries, did recovery at 30 foot at the perch water table. We did recovery down on the 100-foot deep water table. We worked with the system and cleaned it up. And in under 2 years, all the wells, shallow and deep, were non-detect. We had a student do a thesis evaluating where the mass went, which process did what. So sometimes you could do the research and figure out all those bits and pieces. Next slide. And we can also look at it over time. So you can go to a monitoring well and you can check to see that the water level came up, the contaminants went down. You could do these sorts of things over time and think about that data. You could do that electrically too. So if we come back a couple of years later and take an image, the part that was impacted got a lot more conductive. And so you're taking resistor out of the pore space by getting rid of the diesel. You made it more conductive. And then we had some evidence of some microbes starting to grow there. And so that would make it more conductive as well. But you can also see that the purple thing in the middle really hasn't changed very much. So we thought that was not part of the system and it was non-detect and it never became interesting. So you could think about this as a one-time image, the same as you would do a direct push boring and get a number, or you can think about it like a monitoring well and look at it over time and watch what the system's doing electrically to think about what the hydrogeology is telling you. Next slide. So our wells, if we were thinking about it over time, you can trench in and you can either put in some electrodes or you can trench in a cable, and then your stick up would be there and you'd have a cable instead of another piece of PVC once you popped off the top of the stick up. And so then you'd plug in and you can watch things over time. And so, you know, in the future, my concept is that you would have then a few wells that are like the normal ones you're using, but you'd have a couple cables around and you'd be able to watch things changing over time and thinking about whether something crossed a property boundary or whether your remediation is working or whether your remediation wall has stuff going underneath it. You could watch it with a scan that would tell you those things, and you can then monitor your site electrically instead of monitoring it with a piece of plastic and a monitoring well. Next slide. So we've got a ton of cool remediation tools now, and the other webinars are going to talk about those, but those tools work if they get put to the right spot. If you can match up the remediation tool with the spot that's impacted in 3D in the subsurface, those things work great. And the general problem is we're doing really cool things, they're just not in the same spot in the subsurface as where the impacts are. And using wells as a technology, there's plenty of research to tell you that that's not a sufficient data density to understand what's happening in 3D sites, especially karst and hard rock sites. This process of doing electrical hydrogeology, you can get enough data to see where to go. It doesn't tell you the full chemistry. It's not a mass spec sitting at the surface. It's something that tells you what the structure of things are electrically. And if you can read those data and pick out what's going on and integrate those data sets, you can get sites cleaned up very effectively. And so my concept is that you'd be digitizing groundwater moving forward and that you could collect these images and deal with the data sets the same as you would do with a transducer sitting out there doing the geophysics of what's the water level doing over time, or a transducer that's doing EC and you're watching the fluid conductivity over time. You could watch big bulk portions of the aquifer over time and see what's happening and using that data to understand the hydrogeology for whether it's a water supply or a contaminant issue. Next slide.
Great, thanks, Todd. This is awesome. I think now start thinking about some of the questions you've got. Just wanted to remind everybody that we've got 4 more case studies coming up. One, bioremediation and in situ chemical reduction of chlorinated solvents at a former dry cleaner site in Southern California. And Lauren Sues is going to talk about in situ thermal remediation under 2 active railroad tracks. This is at the Brandywine site. And not only did they have to deal with the remediation in the railway tracks, public roadway system, private and government land-owned, wetlands, they also need to make sure that they were meeting the stakeholder needs and the goals of the performance-based contract. And then, also next week, the second last one is managing complex sites with deep multi-level characterization, and that's at Fort Ord. Looked like there was 2 plumes from 2 different sources, and then I'll let the case study discuss how they actually discovered what really was going on in that deep plume. And finally, Todd is going to give another talk of a dry cleaner site where they did a remediation and injection and then scanned it to see how well the remediation was working. So thanks again, everyone. Todd?
Next slide. So we'll go to questions here, and we'll see how that all works. And if you need to duck out at some point, you're more than welcome to, but we'll also stick around and keep answering questions as you guys have them.
So Todd, we have a few questions. One is the webinar being recorded? And will it be distributed to attendees later?
It is being recorded and will be distributed. There's also handouts available on this webinar, and then we have additional handouts that can be distributed if you got other questions. So both answers are yes.
Second question is, can Aestus GeoTrax model zones of recent bioactivity impacts to karst groundwater from chicken litter leaching?
So we've looked at litter leaching, whether it's from a hog farm or a chicken farm, is interesting because when I first started looking at that, you need to understand what happens electrically, and you think, okay, I'm applying fertilizer, I'm applying, stuff coming out of a chicken or a hog, and it turns out that that material actually isn't a great fertilizer, it's a metals waste, and what comes out of those animals has actually got fairly high metals content. So you're distributing that, and you're adding, what you add is a conductive signature to the soil if the metals build up enough. But in terms of being a biosignature and looking for bioblooms, it tends not to have great bioblooms. So you have to think about what the waste is doing and where you're looking as to what signature you're looking for. So a lot of times in karst systems, if that doesn't give you a big biobloom, what you're looking for is where's the fault or fracture or cave, and being able to go in and tap into those zones. On this site we just talked about, the driller had a problem because we were targeting the zone so nicely that they weren't expecting sort of the mush that we were giving them in the fracture zones, because they were so centered into it that they were having a little trouble placing wells. We got another site where our client, for his site, he just goes in and pre-packs the wells, because in the karst setting they're getting so targeted that they can't get a well built, and they just do a pre-pack instead to put it in the conduits. So if you're being able to target, you might have to deal with your remediation slightly different ways, but it's thinking about what the process is, what happens electrically, and then how do you solve it.
Thanks. And if you have follow-up questions or want to talk in more detail about these sorts of things, we're available at the contact information on the screen. Next question is, what is the maximum depth that can be scanned with UHRSC?
So the deepest of all time was the crustal boundary, and that was a friend of mine in South Africa. So that the physics isn't the limit. Its length ratio is 5 times longer than its deep. So if we want to look down 100 feet, we're 500 foot along. If you want to look down 1,000 feet, you're about a mile along. And so we've looked down with mile-long lines and things. It's just, you can't do that every place. But for industrial facilities, like doing the engineering, and you need to go over a waterway, you just float them. If you need to go through a building, you just drill to the side and keep sending your electrodes. And so doing the engineering of setting these lines up, yep, they're straight lines and they're kind of long on environmental sites. but we've set up the engineering to put them through them basically in whatever geometry you need to do, and you make adjustments. But your depth ratio is 5 to 1, 5 times long versus 1/5 deep.
Great. And then another question on the geophysics side of things. Have we considered enabling IP versus the res IP on the SuperSting? There's a good correlation of LNAPL and DNAPL chargeability and weathered plumes.
We have, and it comes down to a logistics issue in that you get that as a good signal on some of them. And so it's how much time do you dedicate to collecting data sets versus being able to collect additional ones and look around. And the additional time is more of a research thing. And so you don't get bang for the buck on all the plumes. And so spending the additional amount of time, which equals additional amount of money, we haven't demonstrated that that's worth it on every site. So that's great on a research basis, and there's lots of things that the geophysics and digitizing groundwater will allow us to do in the future as you figure out what works on a technical basis and what works on a commercial basis and what you can do logistically. But right now, it adds too much time without a guarantee that it's going to provide information.
Thanks. Next question is, I assume your focus was LNAPL at this site in the case study today, versus, as opposed to dissolve phase plume coming off a diesel spill. But could that purple blob that was non-detect for LNAPL have been in an electrically conductive zone due to bioactivity degrading the dissolve phase plume?
And that's what we're worried about. But in sampling that for dissolve phase, nothing ever showed up in that well. And so we think about that on sites. And we've had fairly young sites that are really highly bioactive, which is you usually wait for the bread to get a bit moldy. And we've had sites that were moldy really quickly. And then we've had sites where they've been trying to get bio to grow and it just won't grow. And it's 20, 30 years later and nothing really wants to grow. And it's too cold or the pH is low or the wrong nutrients. And so we've looked at a lot of bioactivity and impacts across a bunch of different sites. And one of the trickiest things is we can see where they grow and that they've got bizarre structures. But in terms of what makes them happy, the more I collect, the less I'm certain as to when they're happy and when they're not. Simple rules only help. They don't guarantee anything about what the bugs want to do.
Adorable dog. Do you need a dog sitter, Todd? Always, right?
That dog is Hemi, and he does like the bed a little too much.
What is the vertical limit of the scan? I think we've addressed that.
Yeah, so we've looked down 1,000 feet plus. Most of our sites, we're looking at, people are interested because 200 feet is not a problem. And if you're trying to deal with hard rock, drilling to 200 feet is a problem and expense. And so then you go, well, I'm going to scan around because that's not super cheap, but poking holes at 200 feet into hard rock is going to kill me. So a lot of our stuff is complicated urban sites where you can't get a drill rig, water sites where, hey, I can't get a rig out there, but you guys can just float the electrodes and take a picture, or hard rock sites where you're drilling costs. They go, I'm definitely going to do this. The other place where people use it is brownfield sites where they've got to get the development going and they can't try remediation, then go, yeah, really not sure what happened. Let's try some other things. We'll sort this out in the fiscal year 2024. When they've got brownfields and they've got schedules, this makes a lot of sense because you can see what's happening and know what's going on and make adjustments and get it done so that you can get the development going.
How many sites has this technology been applied at?
A couple hundred. So we've looked at 60, 80 LNAPL sites. We've looked at 30, 40 DNAPL sites, and then we've looked at water supply sites, salt spills, different combinations of pipeline things and chemical plants.
And we should mention, we've done that worldwide. So most of our sites are in the US, but we've worked in Asia and Australia, South America, Europe. How deep into the ground are the electrodes set? They're
deep enough to get contact. So similar to going to the doctor and they hook some things up to you, the doctors tend not to use stakes because people don't like them as much, but we're just trying to get electrical contact with the skin of the earth. So typically goes in about a foot and we get good enough contact. So not particularly deep. If you're putting in a cable long term, you can either set those electrodes and then come back and hook a cable back up to them, or you can direct bury a cable, and that way you just have to plug in the end. You don't have to worry about it changes the expenses to the trenching and the cost of the cable versus the personnel cost of coming out and hooking back up and doing those things. You can also build a building over it. And so if you need to go and, hey, I need to watch under this building, but they need to get it built, but I know I need to watch it over time. You put a cable under it, you build the building, and then you can still watch underneath the whole building and see what's going on.
Next question is, does a high resistivity layer, especially near the surface, mask what's beneath it, and how does urban piping, et cetera, interfere with measurements? Do you find the EM signal return or screened by silts is the companion? I'm sorry, those are two different questions. So high resistivity layer interference.
Yep. So what I find is most difficult is extreme differences in resistivity. And so if you're looking at a resistive site, that's pretty easy. If you're looking at a conductive site, that's pretty easy. It's if I'm looking at resistors with strong conductors. And so it'd be, I'm looking at a PCE plume with a really resistive NAPL body and microbes that are chewing on it, which are really conductive in those cases. So it's that contrast and which geometry they have. The technique we developed was built to make drillable images. And so the goal for the imagery was, hey, can I make sure I can get a target on this and see where the ground's different? You can set up different geometries that make it a little bit harder, but we've punched through a bunch of geometries that other people have not been able to do with standard approaches that they've used.
Next question is, do you find your EM signal return are screened by silts? Yeah,
so that's basically a conductive question of if it's superconductive. So we've done this in salt plains with freshwater discharging through salt flats, and we could get the pictures to come back and show us where the springs were originating from. So we've tried this in dry granite, we tried this on salt flats, we've tried this with every kind of combination, and we beat the technique up to make sure that we could get a good data set in return so that essentially the drill rig could go anywhere, right? So you want your drill rig to be as flexible as possible. And so we've built this to be able to go over water through buildings and get to places where people need good environmental data.
Has this been applied to heap leach processing as used in the mining industry?
It has, and so we did a study with University of Nevada out on a heap leach site, and we're trying to figure out whether it goes through fairly uniformly or whether it kind of wants to go around the big chunks. And so with the heap leach operation, you get the big chunks versus the small chunks. We were trying to understand how well does the flow go through there to kind of get really focused down. It actually distributed much better than I thought. You basically then just lay a cable up on the top of the heap leach. You start running your cyanide, and you can watch where things are going, and you can make an adjustment if you go, okay, this part of the pile is staying too dry. We've been working with how do you set up all the logic to be able to steer with it, right? So whether you're steering an injection or an infiltration experiment, how do you steer with that and most effectively, in terms of the operations of it, getting the images back and working with that. So very similar to when they first started working with thinking about CAT scans and what you can do for brain scans of when people are doing things and thinking about things. That's the temporal work over time and how to work with that to inject materials and to do infiltration things. There's a bit of complexity that comes in as you start doing that with managing data flows and interpretation of things. But we've done that on heap leach. But thinking about temporal work, there's a ton of research left to do about how to manage that and how to deal with the data most effectively.
And Todd, I think that's it for the questions.
Well, I appreciate your attendance and great to have you, and give us some feedback on things you thought were useful or things you'd like to change, or did you want a longer one or a shorter? Shorter is going to be too hard, but was the shortness of trying to get it in 30 minutes the useful part for you? And some of that feedback would be really useful for us if you can give it to us. So really appreciate your attendance and look forward to seeing you next time.
Thanks, everybody. I'll go ahead and close the webinar. Have a great rest of the week.